Hi everyone. So this week we'll be studying a new class of problems called optimization, which finds application in many different areas of business. So luckily Excel provides a simple and elegant way of solving optimization problems, and this particular Excel capability called solver will be the focus of this session. So in this session, we'll study the logic and nature of an optimization problem. We'll try to identify the key elements so that we can solve the optimization problem. So the solution can be the solution part of it can be done through algebra. That will be the basic construction of a problem, but of course the focus is on how to use Excel to solve it. So once we find the optimized solutions, then we need to interpret what they mean. Um, but also we need to understand whether changes in the different elements of the problem will actually affect the solution themselves. And this can be done through a very useful technique called sensitivity analysis. So the most important Excel skill that we'll be learning here is solver. Solver is an Excel add-in. It's usually not in the core set of Excel. You need to activate that, but it's a very important tool for data analytics. And we also going to use other Excel capabilities such as range names and a function called sum product throughout this whole session with solver. So before we start, we need to take some additional steps so that we'll be ready to use these additional Excel functions. So the first thing is to enable something called a solver. Solver is an add-in. It's actually included in Excel when you download Excel, but most cases, I believe the solver is not activated. I'm not sure why Excel almost always requires you to go through this step. I guess Solver is a pretty specialized program, so they found that most people would not use Solver, so they didn't really want to make the system too cumbersome or too complicated. But in this case, you need to activate Solver. So just have to go to the developer ribbon, which we activated last time, and then select Excel add-ins and then check for the solver item. If it's not checked, then you have to if it's not checked, then you have to check it. So that activates solver. So just do that, take that step and close it. There's also something else that's used in this session called solver table. This is an add-in written by one of the authors of the book, and you just have to download it from the book site. It's actually listed uh, on Canvas, but also on you can find the instruction on page 593 of the book. You can follow the instruction and install solver table, or I find it easier just to put the file in a special folder so Excel can easily see that. So in Windows 10, then the folder is in. So if you go to Windows Explorer, and then you find the file. So you just have to go to the file directory users slash your username. So for instance, my username is DHUANG, so it's users slash DHUANG, and then in app data, roaming, Microsoft, and then um, in the add-ins folder, and just put that file in there. And once you do that, then when you go to the Excel add-in on the developer ribbon, then you will be able to find solver table, and you just have to select it or check it, just like how you activate solver. So this should be pretty easy process. But if you don't want to try to find this folder, which is admittedly buried deep in the Windows folder, the file structure, then you can just make sure that you know where this program is, or this macro is, and then just follow the instructions in the book, and then you will be able to activate it too. So before we apply those Excel functions to optimization problems, Let's ask ourselves what optimization is. Well, an optimization problem always involves maximizing or minimizing a function. And how do we actually maximize or minimize a function? Well, there are different input values that we can choose, but the input values may not vary randomly. So there are probably only an allowed set of input values that we can choose from, and see what combination of the different input values will give us the optimized or maximized or minimized values of the function. So let's take an example. So every morning you leave home, go to work, and you have to commute to work. You have to drive to work, and you want to optimize your commute. And in this case is a minimization of your commute time. So the function. So the function that you're talking about for optimization would be your commute. So why is that a function? Well, there are many different roads that you can take, and every time when you hit the traffic light, then you can decide whether you want to go straight, whether you want to turn left, or whether you want to turn right, right? So that's why it's really a function of different values. Whenever you see a traffic light. So the objective function. So using that example, then we can see what are the three key elements of an optimization problem. So the objective function is the function to be minimized or optimized. So in that example, you're minimizing your commute. So the commute time is the objective function. But the commute time is determined by all of the decisions that you make when you hit the traffic light. So those are all the decision variables. So you can decide whether you want to turn left, whether you want to go straight. So those are all the variables that can take on different values, and that will affect. So the different values will affect the outcome of the objective functions. But not every time when you hit a traffic light you can make the simple decision of going straight or left or right. Sometimes maybe sometimes a road may be blocked during the day, or the congestion may be different, or the traffic may be different on different roads, or some roads are actually one way, so you can't turn. So those are the constraints. So the constraints must be satisfied before you can pick the decision variables, because all the variable values may not be available to you. So the constraints may be in the different forms, maybe physical constraints that you simply can't go straight when it's a T intersection. So for instance, that's a physical constraint. It's a logical constraint is that most of the time, unless it's a traffic, but if you're going south, then you may not want to turn north. So for instance, and there's an economic constraint. So economic involves usually the monetary decisions or the financial decisions. So sometimes maybe you think that when you take a turn, when you take a right turn, you may be faster, but you may be actually a big detour. So that will cost you 3 more miles, and in terms of the spending on gasoline, so you may not want to spend those 3 extra miles of gasoline on that. So depending on the nature of the problem, you'll come up with a set of constraints that will limit the different values of the decision variables, and then you can use the remaining allowed set of variable values to find the minimized or optimized value for the objective function. And that is the nature of optimization problem.